My name is Sergey. I'm going to present you our work on profile inference. This is a joint work that I've done at Facebook with my colleagues, Wenlei, Julian, Lei, and Hongtao. Okay, so the area that we are working on is called profile guided optimization, or PGO. I assume most of you are familiar with this technology, but I can give you a brief overview. So the PGO is a way to build and optimize binaries. And the idea is to split the conventional compilation process into two phases or passes. So in the first pass, we just build a first version of the binary and then run it on a set of representative benchmarks, or deploy it in production workload and run it in a data center. And we learn how this binary works in production. We try to understand what are the hot functions in the binary, what are the frequently executed instructions, and so on. And once we have this information, we run the second compilation pass. But now a compiler can do its job more selectively and more efficiently, and we can produce a faster binary. And PGO currently is a part of most modern compilers, and it produces very large performance benefits. And not surprisingly, most large companies are using some form of PGO. So our work is motivated by the observation that the quality of profile data that we collect can be suboptimal. It can contain some inaccuracies, some errors, some problems, but we still want to use profile guided optimization in the best possible form. So we try to improve the quality of profile data. And this is the topic and the goal of our work. So my talk will roughly consist of three parts. So first of all, I will try to motivate the problem, and I'll actually explain what the problem is. Then I will talk a bit about theoretical aspects of the problem, about a way how we formalize this problem in a graph theoretic way. And finally, I will explain you practical implications of our approach. So let's start with the brief introduction. The first question that we need to answer is to understand why do we even need a high quality profile data. And to answer this, we run two sets of experiments, where in both of the experiments, we roughly built a binary using the precise or high quality profiles and low quality profiles. And in the first experiment, we employ so-called instrumentation-based PGO and compare it to sampling-based PGO. And we see that just by improving the quality of data, we already get some benefits, some performance wins, even though the underlying optimization passes in a compiler, they stays exactly the same. In the second experiment has the same flavor, but here we use a so-called post-link optimizer. And again, here we can get a high-quality profile data almost for free. And we see that if we use this high-quality profile data, we get sometimes even double-digit performance boost, which is great. So now I think most of you should be convinced that the problem is important. And let me try to actually explain what I mean by profile data. So in theory, we have some binary, and we represent it as a control flow graph, for example, consisting of basic blocks and jumps between those basic blocks. And in theory, profile data would be just a sequence of executed basic blocks, right? So we run the binary and we just record the order in which the basic blocks were executed. Of course, this information is hard to deal with because the sequences can be quite long. So people started to look at how to aggregate this information. And the useful concept here is what I call a weighted control flow graph, where instead of storing the entire sequence, we will be just storing the hotness or frequency of each basic block and of each jump. In practice, however, collecting this entire sequence of executions is pretty hard and computationally expensive. So people invented what is currently called sampling-based PGO, where we run the binary and stop it every now and then, and we record what is the currently executed basic block. As a result, what we get is an incomplete weighted control flow graph. So we still have hotness of some basic blocks, but we do not, for example, record the frequencies of jumps. And the process of converting this incomplete data set into the original weighted control flow graph is what often called profile inference or profile correlation. And this is the problem that we are trying to solve. And I hope you're already convinced that this is indeed an important problem. So now let me talk briefly about the problem itself and why is it actually non-trivial. So first of all, while doing the sampling and while applying the sampling-based PGO, we lose some information. And there is what we call sampling and hardware bias. When some blocks, for example, B5 in this figure, it doesn't get any samples, right? It wasn't sampled during the execution. However, we do know that it was executed at least once because its successor B6 was sampled. Right, so fixing this discrepancy is one of the goals of the profile inference technology. So the second challenge is actually even more annoying because this example shows that there is not always a unique way of reconstructing the original data. Right, so in this figure, I show you two control flow graphs, and all the basic blocks, they have exactly the same frequency, but the frequency of jumps here is very different, and the control flows are here very different. So on the right, we see a very hot loop, while on the left, we don't have this hot loop. We instead have a very hot chain of 4 basic blocks. And again, it's up to the inference algorithm to decide what is the correct control flow graph in this instance, in this example. And finally, there are also a challenge of what we call dangling basic blocks. So dangling basic blocks are those that do not have any information associated with them during the profiling phase. So the problem here is that we collect profile on heavily optimized binary, while when we consume this profile, we actually need to associate the counts with the intermediate representation of this binary. And this mapping is not always possible, and this mapping sometimes we cannot do this mapping, so some blocks will not have any information. And again, it's up to the algorithm to decide how to distribute the counts and how to distribute the flow among those dangling basic blocks. So now let me switch to a theoretical approach, how we actually model this problem and how we approach solving this profile inference problem. So in our model, we assume that the input is a control flow graph that consists of basic blocks and jumps between the blocks. And we also assume that some, but not necessarily all, of the basic blocks, they have some frequencies or some estimated counts. And finally, we also assume that the input comes with branch probabilities. For example, for this branch in the figure, we can estimate using some, for example, machine learning techniques, we can estimate that the back loop edge has a much higher probability being taken than the exit branch from this loop. And this information will be helpful to build this unique solution for the problem. So the desired output consists of frequencies of the basic blocks and jumps in this control flow graph. And we call them vertex and edge flows because, of course, the sum of incoming frequency for every basic block must be equal to the sum of outgoing frequencies. So there should be some kind of a flow conservation rule. And the goal here is to infer the most realistic edge and vertex flows given the input estimations. So we started to look at this problem more carefully, and a couple of bad news. So first of all, this problem turns out to be computationally hard, and it's not just hard to find an optimal solution for the problem, but it's actually hard even to find a solution that is approximately optimal. Another bad news is that existing approaches or existing heuristics do not quite work, and they do not produce satisfactory results for many real-world instances. For example, we looked at integer linear programming approaches, and they turned out to be very slow. And some existing heuristics, they often produce just invalid flow values. So with this in mind, we designed and we implemented a new algorithm that we call Profi. So Profi is originally motivated by the classical minimum cost maximal flow algorithm in a graph. However, in order to make it work for our binaries, we had to re-engineer and basically replace all the components of the classical algorithm. So I'm not going to give you more details about the algorithm, but if you are interested, we can talk offline. I'm really proud of this algorithm. And now let's talk about practical implication. I wanted to emphasize that our work and our algorithm is currently a part of the LLVM compiler, and it powers one of its PGO frameworks. So implementation-wise, profile inference component is a post-processing step that is applied to collected profile data. So it's fairly easy to remove it or improve the implementation. And of course, we also tested how our algorithm affects the speed of generated binaries. We tested a few real-world Facebook workloads, and we often get 3-4% speed ups. And we also tested the algorithm on open source binaries and open source benchmarks. And again, we see some very good numbers. As I mentioned, the algorithm is quite efficient, even for very large instances that contain thousands of basic blocks. Our runtime is below a few milliseconds. And last but not least, I wanted to tell you where are we now in terms of overall quality of profile data. And for this, we had to invent a metric that is some number from 0 to 1 that quantifies the quality of the profile data. So ground truth profile data has a value of 1, and some random numbers, some random profile will be get a value of 0. So currently with our algorithm, we are at something like 0.9 or 90% quality. So there is still a gap. So we are still not quite operating with the exact profile, but I suppose this is one of the opportunities for future work in this area. Okay, let me conclude my talk. I think two important contributions of our paper. So first of all, the quality of profile data is very important. So if you care about the performance or efficiency of generated binaries, then we need to invest time into improving the quality of collected profiles. And another contribution, which I consider equally important, is our new formal optimization model that we call profile inference problem. So we just scratched the surface and we only studied very basic properties of this problem. I assume there will be a lot of interesting follow-up theoretical works in this space. And for the future, there are many different directions. My favorite one is to try to explain why, despite the theoretical hardness of the problem, we still can get reasonably good solutions in practice. And here we may be looking at some specific structural properties of instances of control flow graphs that we are working with. For example, we can look at tree width of the graphs that we're working on. And with this, thanks for your attention, and I'm happy to answer questions.
Thank you. Thanks a lot. So do we have any questions from the room? Yes.
Hi, it's Eric Atkinson from MIT. I was just curious if, so it sounds like you're giving point estimates for the edge and basic block frequencies. And I was wondering if there's any need in the optimization community to quantify the uncertainty in those estimates and incorporate that into the optimizations. I'm not sure, have you seen anything like that?
That is a very good suggestion. I personally have not seen any compiler optimization path that would employ some uncertainties, but that's probably one area that we can look into in the future. Yeah, that's a good one. Yeah, I don't know.
Let's see, do we have any other questions here in the room? If not, are there any online? All right. So in one of the results that you showed at the end, I guess there were a couple of applications. One in particular where there was a small slowdown. Was there anything special about that application that made it less suitable to this, or should we just think about it as noise?
Yes, that's indeed a very good observation. The regressions that we typically see happen on smaller binaries that contain only very few functions, and where some change in the profile data or in the optimization path can actually affect the overall performance. So in this space, we improve the quality on average, but of course there will be some instances, some special corner cases where the quality regresses or where we make some mistakes. And for smaller binaries, those mistakes can actually result in noticeable regressions.
All right, thank you. Oh, we do have one more question. So, did you compare the profile inference technique against profiling with exact counts instead of sampling?
Yes, in one of my actually first slides, there was this comparison. And in the paper, there are some details. We are closing this gap. So we're still not quite there yet. So still, if you use the exact counts, you can get better results. But we significantly close the gap with the instrumentation-based counts. But yeah, there is still some work to do here.
All right, thank you. So let's thank the speaker. And that concludes our